Welcome back to Very Ordinary Differential Equations. In this lecture, we apply our new skills using power series to solve differential equations to second-order equations. So now we have our second-order linear homogeneous differential equation where all of the coefficients are polynomials. Furthermore, we're going to assume there is no common factor between the three polynomials, or equivalently, there is no shared root between all three polynomials. If there were a shared factor of the form x minus a, then you could cancel it out from all three terms before you even started the problem. So what follows is that if x naught is not a root of the leading coefficient, in other words, x naught is an ordinary point, then any solution can be represented as a power series centered at x naught with a positive radius of convergence, and we're going to be using the same techniques we did in the previous lecture. So let's just dive straight into an example. Find all solutions to the equation x squared minus 1 times y double prime plus 3x times y prime plus y equals 0 as power series centered at 0. As always, we check the place where we are centering our power series is not a root of the leading coefficient. Therefore, we're at an ordinary point and we're going to be fine expressing solutions as a power series centered at that value. So here is our generic form for a power series centered at 0, and we assume y takes this form. Then we just have to start computing various terms to go into the differential equation. For example, y prime, and again, we take a derivative, but the constant term has derivative 0, so it gets removed from the expression. And then 3x times y prime, which is what we actually have in the differential equation, will restore that power. So instead of being x to the I minus 1 and not matching this index, once you multiply every term by x, it becomes x to the I. Also observe that we have 3i, ai x to the I, but the series starts at 1 because the index 0 term was the constant term, its derivative was 0, and it was removed at this point. However, this expression, if I equals 0, would itself be 0, so it can be freely added back into the sum at no cost. So here is our expression for y prime before we multiplied by 3x. If I take y double prime, well then, the index 1 term corresponds to the constant term. Its derivative will be 0. So when I take two derivatives, I equals 0 and I equals 1 are both removed from the series, and we now begin at I equals 2. And when I take two derivatives of x to the I, we get I times I minus 1 times x to the I minus 2. However, this series, beginning at index 2, is not going to be ideal. We want this power to match this index. Observe that at I equals 2, this power is 0. So in re-indexing, I can begin at 0 and make the power the same. I then just have to adjust these occurrences of I as well. Since this got increased by 2, all of these do as well, and we have I plus 2, I plus 1, ai plus 2. This is the power series for y double prime, which we will use here in the minus 1 times y double prime. But what about the x squared y double prime? Well, y double prime was right here. This was the series starting at index 2, but with this power of x being x to the I minus 2. If we just take this series representation and multiply by x squared, the power is immediately restored because x squared times x to the I minus 2 will itself become x to the I. But now I have a series beginning at index 2, and in order to combine it with all of the other terms we have here, I'd like to have it begin at index 0. So let's just check. The missing terms in this series are index 1 and index 0. But if I equals 1, then this would be 0, so I can add that back in without any concern. And if I equals 0, then this term here is 0. So I can add that term back in freely at no charge as well. So because I equals 1 and I equals 0 would produce zeros here anyway, I can go ahead and reincorporate I equals 1 and I equals 0 into the sum. So instead of going from 2 to infinity, I can make it go from 0 to infinity. The terms I just added back in are 0 anyway. So now, x squared y double prime and y double prime both have power series beginning at index 0 with the term x to the I, and on the previous slide we already had a power series for 3xy prime that did the same. So here was y double prime and x squared y double prime. Therefore, I can take the difference, x squared minus 1 times y double prime will be this power series minus this one. They have a shared factor of x to the I. That was always the objective in our re-indexing, so I factor that out. And I will have I minus 1 ai, minus I plus 2, I plus 1, ai plus 2. So x squared minus 1 y double prime is now expressed as a single power series with this fairly nasty looking coefficient. So here was the power series we had for x squared minus 1 y double prime. Earlier, we found these power series for 3xy prime and the basic starting power series for y, and now I can add all three of these three things together. So x squared minus 1 y double prime plus 3xy prime plus y is now expressed as this enormous coefficient times x to the I. Because all of my power series had been re-indexed if necessary to make x to the I appear, and also all of them had the same range of indices from 0 to infinity, I combined them quite nicely. Here was what we had from our x squared minus 1. Here's the coefficient for 3xy prime, and here's the generic coefficient just for y. So here's our power series that represents our differential equation. Simplifying a little bit by collecting like terms. Okay, so how many ai plus 2's do we have? Negative I plus 2, I plus 1 of them, right there. But how many ai's do we have? I times I minus 1, plus 3i of them, plus 1 of them. I times I minus 1, plus 3i plus 1 times ai. Therefore, since this power series represents a converging power series on an interval because we were at an ordinary point, which is always equal to 0, all of those coefficients must themselves be equal to 0. So we've just deduced this formula for the coefficients of our generic power series solution. We can solve this for ai plus 2 in terms of the previous ai. So ai plus 2 is now this expression times ai. Simplifying the numerator becomes I squared plus 2i plus 1, which factors as I plus 1 squared. So I have I plus 1 squared up here in the numerator. I can cancel that with this I plus 1 down in the denominator. And we find that ai plus 2 is I plus 1 over I plus 2 times ai. So far what we've determined is that any power series solution, y equals the sum of ai x to the I, the coefficients ai satisfy a relatively simple recurrence relation. ai plus 2 is I plus 1 over I plus 2 times ai. So whatever the value of a sub 0 is, a sub 2, by letting I equals 0, we get a sub 2 is 1/2 a 0. By letting I equals 2, we get a 4 equals 3/4 a 2. By letting I equals 4, we get a 6 equals 5/6 a 4. So a2 is 1/2 a 0. a4 is 3/4 what we just found, which becomes 3/8 a 0. a6 is 5/6 what we just found, or 15/48 a 0. All of these even terms are now going to be expressible as some number times a 0. We just need to come up with a formula for that number. Notice, if I have a sub 0 here, then this numerator was odd. If this I is any even number, then this is I plus 1, it's odd, and this denominator is even. So if I start from a0 and I generate a2, a4, a6, etc., these numerators are just a sequence of odd numbers, and the denominator is a sequence of even numbers. So we are multiplying all of the odd numbers up to 2i minus 1, then divide multiplying all of the even numbers up to 2i. And if you've never seen this double factorial notation, it simply refers to take this number, and a single factorial would be multiply every integer all the way down until you hit 1. The double factorial notation means multiply by subtracting 2 every time. Okay, so for example, 8 double factorial would be 8 times 6 times 4 times 2, but you stop before you hit 0. 11 double factorial would be 11 times 9 times 7 times 5 times 3 times 1, and then you stop. So this would itself in the numerator be the product of all the odd numbers up to this one. This denominator is the product of all the even numbers up to that one. So here is our nice formula for a sub 2i. It's always expressible as this number times a sub 0. So we now know exactly how to represent all of the even indexed coefficients. Which of course leaves a question, what about the odd index terms? Well, whatever the value of a1 is, we find these following values for A3, and then A5, and then A7. Now the numerator, in our recurrence relation, the numerator was 1 larger than the index of the AI on the right. So if we have odd indices here, our numerators are now even and our denominators are now odd and 1 larger. So we end up with this expression right here. Okay, so to get a sub 2i plus 1, we're going to end up with all of the even numbers up to 2i divided by all of the odd numbers up to 2i plus 1 times the original value of a1. So whatever the power series solution is, we have these expressions that tell us the value of the coefficients. All of the even index coefficients can be expressed in terms of some multiple of a sub 0, and all of the odd index coefficients can be expressed as some number times a sub 1. So in our sum, our power series sum, a0 plus a1x plus a2x squared, etc., we're going to break it apart into two sums, the even index terms and the odd index terms. So we'll have our even index terms, and then we will have the sum of all of our odd index terms, expressed like this with our series notation. So instead of just listing out all the terms at once, we have the even ones, and then we add in the odd ones. So here is how we represented y as a sum. We took its power series and broke it apart into the even index terms and the odd index terms. And we did this because we have these formulas for the even index terms and odd index terms, respectively. Now we're going to take this expression for a sub 2i and plug it in here. And notice that every single term now has the same constant of a sub 0, which can then be factored out of the sum. Similarly, when I substitute this expression in for a sub 2i plus 1, this same constant of a1 will appear in every term and can be factored out of the sum. So we can write it just like this down here. And I want to point out that this very closely matches how we expect to present general solutions to second-order linear equations. We have some unknown value times one function. Whatever this power series is, it is some function of x. So we have a constant, which we don't know, times f of x, plus another constant we don't know, times some other function. In other words, any solution to the differential equation is now expressed as a linear combination of this power series and this one, which is to say these two power series, once you show they're linearly independent, form a fundamental set of solutions to our differential equation. So this does match the format that we've been finding solutions. Some constant times one function plus another constant times another. It's just that those two functions are not something nice and clean in elementary form like sine x or something like that. It's just a power series, but there it is. So let's move on and try another example. Find the fifth degree Taylor polynomial centered at 0, approximating a solution to this initial value problem. In many scenarios, in practical applications, an exact solution is not necessarily feasible. You may only be interested in a close enough approximation. And when you're doing a close enough approximation, Taylor polynomials are often the name of the game. So here we're going to try to find a fifth degree Taylor polynomial centered at 0 to approximate a solution to this differential equation. So what we have to do is express the solution as a power series, and then to get the fifth degree Taylor polynomial, we simply determine the coefficients a0 through a5. X equals 0 is not a root of that leading coefficient 2 plus x. In other words, we're at an ordinary point, so we can express y as a power series. We can then compute y prime and y double prime. Notice that the starting index changes. It gets shifted up by 1 every time you take a derivative. So here are our generic power series for y prime, and y double prime. Of course, in our problem, we need a negative 3y, so multiply this by negative 3. We need a 1y prime, but we also need an xy prime. So here's xy prime. Simply take this series and multiply everything by x, raising this power. Similarly, we need an xy double prime. So here's this series, multiply by x, and the power gets shifted up, but just by 1. So here were y prime, y double prime in their generic form. We already found xy prime to be written like this. When possible, it's nice to have all the series start at the same index. So can this begin at index 0 instead of index 1? Sure. Okay, at index 0, this formula predicts 0 anyway, so you're free to add that back in. Okay, but here's y prime. this power series here, simply shifting the index to make x to the I match the index starting at 0. So here's xy prime, here's y prime. We need both because in our differential equation, we need a 1 plus x y prime. So we need a y prime plus an xy prime. And here we have it. 1y prime is given here, I plus 1 times ai plus 1 times x to the I. xy prime has iai, x to the I. Add them together and factor out that x to the I, and here we have a power series for 1 plus x times y prime. 2y double prime is straightforward enough. Here was our power series for y double prime just multiplied by 2. As always, we want to re-index our power series so that the power of x is simply I. At I equals 2, this starts at a power of 0, so we go ahead and do that. Starting it at a power of 0, we make that x to the I. Since that involved increasing this by 2, we increase all of these by 2. So here is our re-indexed power series for 2y double prime. Earlier, we had a power series for xy double prime. It was as such. We need to re-index this, okay? Since this is x to the I minus 1, at its first term, we have x to the first. So we're going to start the series at 1 and make that our power of x, x to the first. I only increased this power by 1, so we increase every other occurrence of I by 1. Now I do have a power series where x to the I appears. That's great. What would be convenient, although not strictly necessary, is for the index to start at 0. And we simply check. At index 0, we would be adding a 0 anyway, so we're free to incorporate that term into the series without changing anything. So now we have a power series for 2y double prime and a power series for xy double prime. Both of them have been re-indexed so that the shared factor of x to the I appears, and conveniently enough, they both start at index 0. Therefore, I can add them pretty easily. 2 plus xy double prime. We get, here is our 2y double prime from up here, plus xy double prime from right here, having already factored out the shared factor of x to the I. So here was 2 plus xy double prime as found on the previous slide. Earlier, we found 1 plus xy prime, and here is the pretty straightforward minus 3y. They are all power series that have been indexed so that x to the I appears as a shared factor, and conveniently enough, they all start at index 0. So I can just add all of them together. So for our differential equation, 2 plus xy double prime plus 1 plus xy prime minus 3y, preemptively factoring out the shared factor of x to the I from all of them, we have, here is what we had for 2 plus xy double prime, plus 1 plus xy prime, minus 3y. This plus this, and then add that one in as well. So we have a big, large expression times x to the I. Here's the power series we have deduced for our differential equation. It starts at index 0 by consistently re-indexing power series as we generated them so that they had this shared factor of x to the I. That all worked out. It's a large expression, but it's just something times x to the I. So we conclude that since all of this is supposed to be 0, because we had a homogeneous differential equation, that this power series must be 0. Since it was centered at an ordinary point, it converges on an interval of positive radius. And if a power series converges to 0 on an interval, then it must have 0 for every coefficient. So every coefficient must be 0. In order to begin computing values of these coefficients ai, we do need some initial values. So here was our power series, a0 plus a1x plus a2x squared, and so forth. Y prime, if I take a derivative, we end up with that. So if y of 0 is a0, if I plug in x equals 0, we just get a0. Similarly, plugging in x equals 0 for y prime gives me y prime of 0 is a1. So we already know that a0 is 1 because we were given y of 0 is 1. And we already know that a1 is 2 because we were given y prime of 0 is 2. So we actually know the first two coefficients. a0 is 1 and a1 is 2. So we already know the values of a0 and a1, but don't forget we have this recursive formula. So if I plug in I equals 0 into this recursive formula, we get 2 times 2 times 1 times a2, plus 1 times 0 times a1, plus 1 times a1, plus 0 times a0, minus 3a0 equals 0. Altogether, 4a2 plus a1 minus 3a0 equals 0. And since we already know the values of a0 and a1, when I plug those in, we can quickly solve that a2 is a quarter. So now we know a0 is 1 and a1 is 2, but we've also deduced that a2 is a quarter. With the same recursive formula, plugging in I1 will give 2 times 3 times 2a3, 2 times 1a2, 2 times a2, 1 times a1 minus 3a1 equals 0, which simplifies down to 12a3 plus 4a2 minus 2a1 equals 0. But again, since we know a1 and we have determined the value of a2, we can now solve that a3 must be a quarter. So now we've determined that a0 is 1, a1 is 2, a2 is a quarter, a3 is a quarter. By plugging in I equals 2 into this recursive formula, we'll end up with 24a4 plus 9a3 minus a2 equals 0. Since we already know many values, we can quickly find that a4 is negative 1/12. And finally, now that we know a4 is minus 1/12, we use the same recursive formula, plug in I equals 3, get 40a5 plus 16a4 equals 0. Since we already know the value of a4, we end up solving that a5 is 1/30. So we have found that a0 is 1, a1 is 2, a2 is a quarter, a3 is a quarter, a4 is negative 1/12, and a5 is 1/30. The fifth order Taylor polynomial to approximate a solution is therefore a0 plus a1x plus a2x squared, a3x cubed, and so forth. With our values, there it is. That is our fifth order Taylor polynomial which approximates a solution to this differential equation. As a third example, let's find a third degree Taylor polynomial centered at x equals 1 to approximate a solution to this initial value problem. Note that x equals 0 is a singular point of the equation. It is a root of that leading coefficient x squared. So we can't center our power series solution there. But x equals 1 is not a root of x squared, therefore it's an ordinary point. So we're going to use a power series centered at 1, as the problem suggests. Now we're going to proceed as before, but we will see that it works slightly differently when our center is not 0. So we start with the relatively direct computation of 3y. It's just our generic power series centered at 1 times 3. Y prime we compute as we have before. So from our generic power series we started with, we take a derivative, and as before, the constant term vanishes, which means this new series begins at index 1. In our differential equation, we want to multiply y prime by x minus 1, which is actually quite convenient to do. If I multiply by x minus 1, since the power series has x minus 1 in it already, I simply multiply by x minus 1. That increases this power by 1. So instead of being to the I minus 1, it's now to the I power. Our power series did start at index 1. However, the formula would predict for index 0, I times ai, that would just be 0 times something. So we can reincorporate that term without any cost. Now here is a general representation of y double prime. When I took two derivatives, the first two terms vanished. Therefore, this power series starts at index 2. Now we're going to use the following algebraic identity. X squared is in fact x minus 1 squared plus 2x minus 1. If you FOIL this out or expand it out, you get x squared minus 2x plus 1, so cancel out the minus 2x and the plus 1. But furthermore, instead of calling this 2x, call it 2 times x minus 1. This would give me 2x minus 2, so cancel out that minus 2 by adding 2, which transforms this minus 1 into a plus 1. You can verify x squared really is x minus 1 squared plus 2 times x minus 1 plus 1. Now, while that's true, why do we care? The objective here is to transform things in terms of x minus 1 rather than x. If I attempt to multiply this power series for y double prime by the coefficient x squared, I can't really do anything with that. Multiplying this by x squared doesn't help me affect this power, because here I have x minus 1 to a power. Multiplying by x squared doesn't help. But multiplying by x minus 1 squared, or multiplying by x minus 1, can easily be incorporated into this power series. So instead of multiplying by x squared, we want to multiply by all of this, things in terms of x minus 1, because that's the general term of our power series. So y double prime can generically be computed as this. If I re-index it directly, by bringing this power up by 2, I can start this at 0 instead of at 2, but I need to increase these appearances of I correspondingly. So here is a power series for y double prime. It can be multiplied by x minus 1 quite easily. Starting back here, for our generic representation of y double prime, if I multiply by x minus 1, I can raise this power by 1. Now I can re-index that, and now I have a series beginning at index 1 of I plus 1i ai plus 1, x minus 1 to the I. I can multiply this by 2 at no problem. I just bring the constant 2 in. Also, this series began at index 1. I would kind of like it to begin at index 0. Can I do that? Sure. At index 0, I would end up with a 0 anyway, so I can freely reincorporate that back into the series with no real problem. And finally, going back to the original appearance of y double prime, if I simply multiply by x minus 1 squared, it just takes this power and directly raises it by 2. As before, I'd like this to not just begin at some other index, but to begin at index 0. The missing terms are index 1 and index 0. Well, if I equals 1, this produces a 0, and if I equals 0, this does. So both of those terms can be reincorporated without any kind of problem, so I just start this at 0 as well. So now we have a power series beginning at index 0 with the proper power of x minus 1 for x minus 1 squared, y double prime, 2x minus 1, y double prime, and y double prime. So y double prime was written like this, 2x minus 1 y double prime as such, and finally x minus 1 squared y double prime as this. And since we have already determined that x squared is simply x minus 1 squared plus 2 times x minus 1 plus 1, instead of doing x squared y double prime, we'll do x minus 1 squared y double prime plus 2x minus 1 y double prime plus y double prime. So this power series plus this one plus that one. So here is how we have re-expressed x squared so that every power of x is actually buried in an x minus 1. Taking all of the power series from the previous slide and putting them together correctly gives us this expression. They all had a shared factor of x minus 1 to the I. They all began at index 0. And here is what we had for x minus 1 squared, 2 times x minus 1 plus 1, y double prime. Now we can combine with the series we found earlier for x minus 1 y prime and 3y. Combining all of those series together gives us this enormous expression. Okay, so our expression for x squared y double prime was all of this times x minus 1 to the I. X minus 1 y prime was just this times x minus 1 to the I, and 3y was just this term here, x minus 1 to the I. So adding all of this together, we have all of this, x minus 1 to the I. And since we now have a power series at an ordinary point equal to 0, every coefficient must be 0. Combining like terms, here are all of our ai plus 2's. It just occurred here in this term here. The only appearance of ai plus 1 was in this term here. However, all of our ai's put together, we have I times I minus 1 of them, I of them, and 3 of them. So I times I minus 1 of them, I of them, and 3 of them. Now, in order to find the third degree Taylor polynomial as the problem requests, we just need to find some coefficients a sub I. A sub 0 is just the function y evaluated at the center, and we were given that y of 1 is minus 2. So a sub 0 is minus 2. A sub 1 is just the derivative evaluated at the center, and having been given that y prime of 1 is 1, a sub 1 is 1. Otherwise, we're just going to rely on the recursion formula that we found on the previous slide. Here it was. Now, in example 2, we took this recursion formula and used it directly. Often, what you'll want to do is solve for the largest index term. The largest index term is ai plus 2. Solving for that will involve throwing all of these terms to the other side, which is where these minus signs come from, and dividing by I plus 2, I plus 1, which expands out as such. Now at I equals 0, this would solve to a sub 2 is 3a0 minus 0 over 2. And since we were given the value of a sub 0 is minus 2, this works out to just be a total of a sub 2 equals minus 3. So we know that a sub 1 is 1 and a sub 2 is minus 3, and here was our recursive formula. If I equals 1, we plug it into our recursive formula and we end up with a sub 3 is 2a1 minus 4a2 all over 6. We know that a sub 1 is 1 and we know that a sub 2 is minus 3. And this works out to be 14 over 6 or 7 over 3. Altogether, what do we now have? Our initial values gave me a sub 0 is minus 2 and a sub 1 is 1. We were then able to use our recursive formula to compute that a sub 2 is minus 3 and a sub 3 is 7/3. So we are well prepared to state our third degree Taylor polynomial, having computed a sub 0, a1, a2, and a3. It's simply a sub 0 plus a1 times x minus 1 plus a2 times x minus 1 squared plus a3 times x minus 1 cubed. And with the values we know, there we have it, our third degree Taylor polynomial approximating a solution to our differential equation with the known initial values. Altogether, what did we do here? The techniques we used are not really different from how we solved first order equations in the previous video. The work is a bit more tedious, however. Once you involve higher and higher derivatives, there's just more work to do. The recursive formulas now get rather complicated and refer to more and more previous terms. So in the first order equation video, all of our recursive formulas were fairly straightforward and referred back to a single term. Here, however, we got recursive formulas that referred to 2 previous terms. Now, what can theoretically happen is you can do this with higher and higher derivatives, third order equations, fourth order equations, and so forth. However, doing these problems by hand, or even just finding approximations to, a reasonable Taylor polynomial, can quickly become kind of overwhelming if you're just working it out yourself.